In this tutorial, we are going to walk through the design of single balance mixer using the advanced design system and extract the most important parameters. Mixers are among the most essential circuit elements in wireless communication, radar, radio, sensors, and all circuits where shifting a signal band from one center frequency to another is required. A mixer is a device with 3 ports, 2 for inputs and 1 for output. Its primary function is to produce an output signal whose frequency corresponds to either the addition or subtraction of the frequencies of the 2 input signals. This slide illustrates the fundamental operation of a mixer, where the radio frequency, RF, signal and the local oscillator signal act as inputs. The resulting intermediate frequency is derived from either the sum or the difference of the RF and LO frequencies. A mixer performs down conversion by shifting a high-frequency RF signal to a lower intermediate frequency for easier processing, typically in receivers. Conversely, it performs up conversion by converting a lower frequency signal to a higher RF frequency, used in transmitters for signal transmission. Both functions rely on combining the RF signal with a local oscillator signal. Here are the key parameters of a mixer. Conversion loss. The difference in power between the input RF signal and the output if signal, typically measured in dB. Lower conversion loss indicates better efficiency. And isolation. The degree of separation between the mixer's ports. High isolation reduces interference and ensures proper operation. One common choice for nonlinear mixer devices is a Schottky diode. It could produce various input signal combinations with the use of its nonlinear properties. This slide depicts the schematic of a single balanced mixer. The design incorporates a hybrid ring coupler, commonly known as a rat race coupler, to combine the input signals. The amplified RF signal is applied to the sum port, while the LO signal is fed into the delta port. The coupler generates a balanced LO output, which drives the 2 Schottky diodes, facilitating the mixing operation. The intermediate frequency signal is extracted from the common junction of the 2 diodes and passes through a low-pass filter to the intermediate frequency output port. A capacitor, C1, is also included to suppress the RF and LO signals at the intermediate frequency output, ensuring signal purity. In this video, we are going to design this topology for a single balance mixer using advanced design system. Let's get started. As mentioned, the first step is to design a rat race. To create a component with sum and differential ports. It consists of a circular transmission line with multiple ports spaced at precise angular intervals, typically separated by quarter wavelength. We need to open a schematic and define a substrate to do that. Here we are using RO 4003 substrate. And bring the microstriplines. Using the curve lines, we would be able to create the phase shift between different ports. The distance between each ports should be lambda over 4, to have 2 ports that have same amplitude but 180 phase difference. We copy and paste the upper side to make a complete structure. But we can delete the port lines. The S-parameter analyzer should be added to check the performance of the structure, and ports should be defined. In this design, 5.7 GHz is considered as a design frequency. Port 1 is input and ports 2 and 3 are outputs. Port 4 is an isolation port. After running the simulation, we can check the S-parameter. Amplitude of S21 and S31 should be equal and close to -3 dB. At the same time, the phase difference between these two ports should be 180 degrees. In order to confirm the performance of the designed rat race, we need to take it to the layout environment and simulate it. To do that, we can use the Layout menu and hit the Generate Layout option. First, substrate should be defined, then ports should be connected to the structure. EM setup adjusting and define the number of mesh and frequency simulation is the next step. The results should not be that much different than the schematic design. We can also create a symbol from this design, in case we want to use it in schematic. To do that, from EM menu we can go for Component and choose the Create model. After designing a rat race, we can use it to design a single balance mixer. First we need to create a symbol from the design rat race. To use it in new schematic, we can add pins and remove the ports. It should be considered that the sum and difference ports that are ports 2 and 3 should be used to connect the diodes, and ports 1 and port 4 are used for RF input and LO port. This design is based on two Schottky diodes. A Schottky diode is a commonly chosen nonlinear component for mixer circuits due to its ability to combine input signals and generate new frequencies through its nonlinear behavior. This property enables it to produce the sum and difference frequencies needed for frequency conversion in mixers. Although it shares similar current voltage characteristics with a standard PN diode, the Schottky diode is based on a metal semiconductor junction rather than a PN junction. This unique structure provides several benefits, including faster response times, a lower forward voltage drop, and reduced junction capacitance, making it highly suitable for high-frequency applications. At elevated LO power levels, the diodes can become unintentionally biased, resulting in undesirable conversion losses and reduced isolation performance. To mitigate this issue, a DC grounding mechanism is incorporated into the design without disrupting the RF properties. This is achieved by using an RF choke. Additionally, two quarter-wavelength shorted stubs, tuned to the RF and LO frequency of 5.7 GHz, are implemented. These stubs direct the intermediate frequency mixing products on the RF side of the mixer to ground, while simultaneously presenting a high impedance at the RF and LO frequencies, ensuring efficient signal processing and stability. So we need extra matching network after rat race for both sides. In this design we have used the SMS7621 from Skywork. The way that we can define the model for this diode has been explained on other videos of this channel. Additionally, a capacitor, C1, is added to suppress the RF and LO signals at the intermediate frequency output. Also, a low-pass filter should be used to have pure intermediate frequency at the output. It can be implemented by a series inductor and two shunt capacitors. We can create a new schematic to check the performance of low-pass filter. We can create a symbol with 3 ports as a mixer to be able to use it in a new test bench. We can create a test bench to check the most important parameters of Design Mixer. In Design Guide menu we can choose Mixer. In Open Window there are different options. We will go for Single Mixer Characterization. In this option there are some items that each one create different test bench to provide different outputs. First, we are going to check the power conversion. There are some parameters that should be set in this window: LO power, LO frequency, and RF frequency. Harmonic Balance Simulator has been used. In this design, we are going to have a down conversion mixer with the 50 MHz intermediate frequency output. Also, there is a sweep plan that is used to sweep the input power. If we push into the mixer symbol, we can remove the circuit and replace it with our design mixer and connect the pins to the specified nets. And run the simulation. As you can see, conversion loss is not reasonable because the LO power should be determined properly. Since the design mixer is a down, up conversion loss is high. As you can see, by increasing the LO power to 15 dBm, conversion loss is around -10 dB, and by increasing the input power it goes to the saturation mode. If we want to check other parameters such as isolation between ports, we need to create another test bench through the Design Guide menu and set parameters, like the one we did for the previous simulation. You can check the isolation between ports in this data display. As you can observe, 36 dB isolation is achieved between LO and RF ports by this design. Also, input impedance of each port have been provided in this test bench. If you are interested in these kind of videos, like this video and subscribe the channel. Thanks for watching.